Okay, honors chemistry. It's good not to see you there, but you are there. This is either going to be posted on Monday the 27th or on Wednesday the 29th, or not at all, depending upon what answer I get from the administration regarding teaching 2 lessons a week from the textbook and teaching 2 lessons a week from ACT Academy. That's my request. That's the way I'd like to go with it, but we'll see. Anyway, turn to page 589. 589 in your hymnals. This is the end of chapter 18, but there are 2 sections in there that are valuable that I'm not going to cover. This is the end of 18-2, and it's the problems at the end of the chapter. I just want to teach you this concept, Le Chatelier's principle, and this is a word you're going to hear in college quite a bit. And how do you spell it? I don't know, something like this. Chatelier. And Le Chatelier, I call it Le Chatelier. Le Chatelier's principle is back here on, oh my, should have had this ready to go. How about page 564? On page 564, we see the French chemist Henry Louis Le Chatelier in 1888 developed his principle, which says, this is on the top of the page in italics, it's 564. If a system at equilibrium is subjected to a stress, the equilibrium is shifted in the direction that tends to relieve the stress. So what does that mean? Well, let's practice. What that means is number 8 on page 589. Number 8 on page 589, number 8. We got an equation, 2NO, and that's a gas plus oxygen gas, yields 2NO2 gas, and it's in equilibrium, so it's reversible. Let me get this thing out of the way. It says, predict whether each of the following pressure changes would favor the forward or the reverse reaction. Okay, so how many moles of gases do you have? 2 plus 1 makes 3. How many over here on the product side? Just 2. So if you increase pressure, on the side that has the greater number of moles, it's going to squirt the other direction. It's like that great big old fat pimple I was talking about. It's bloated. You need to relieve the pressure, so it's going to go the other direction. Basically, the haves go to the have-nots. The 3 goes to the 2. If you increase pressure, it's going to go that direction, forward. Is that a good thing in industry? Well, if you're making NO2 gas, it really is, because you're going to get more product before equilibrium sets in. And so it's going to favor the right side. It's going to favor the forward direction. And the K value, the equilibrium constant, is going to be big. So that's what you're looking for. So in a system like that, you're going to increase pressure. But what if you decrease pressure? Well, just the opposite is going to happen. It's going to create what I call a suction. You know, like decreasing the pressure in a straw, sucking the air out of the straw. Does it flow right up the straw? So if you decrease pressure, it's not going to go forward. It's going to go in reverse. It's going to go this direction. I guess that's kind of like sucking the air out of a straw. You're going to pull it anyway in this direction. Okay, so you're looking at it from the viewpoint of the side with the greater number of moles. If you increase pressure, it's going to squirt that way. If you decrease pressure, you're looking at the same side, it's going to suck this way. Le Chatelier's principle, you're going to hear that term used constantly in college And I wanted you to hear it here first. Number 9, in a heterogeneous reaction, what types of substances do not appear in the equilibrium constant expression? Pure liquids or solids. You can't change the concentration of the pure liquid or the solid. And so since the equilibrium expression is dealing with gases primarily, and I guess you might say aqueous solutions, because you can change the concentration of aqueous solutions. It's pure liquids that you can't change. Number 10, explain the effect of a catalyst on an equilibrium system. Well, the catalyst will speed up the reaction, but will not change the value of the equilibrium constant. Okay, you don't get more product or more reactant. You simply get what product you're going to get based upon the prediction of the equilibrium constant. You get that product faster. That's all a catalyst does. It doesn't give you more, it just makes it happen faster. Number 11, predict the effect of each of the following on the indicated equilibrium system in terms of the direction, forward, reverse, or neither. Which way will it drive? So we got hydrogen gas, number 11. It's a gas, and we're combining it with chlorine gas. And we're making hydrogen chloride gas. And we're releasing 184 kilojoules of energy. Now, instead of writing the equation like that, with 184 kilojoules, you remember that we could have just gone like this. Change in enthalpy is negative 184 kilojoules. Either one of these expressions means exothermic. Heat is being released. You can either use that as a product, or you can say that the negative sign indicates that heat is being released. Either one of those expressions, one or the other, but not both. And so why is it positive? Why is it negative? Because this time it's a product, and this time it's just an expression of delta H. It's exothermic either way you write it. Okay, so you're releasing heat going in the forward direction. So you're going to add more Cl2. Anytime you add more reactant, you get more product. And you drive to the right. In this case, this is a reactant, so it's going to go forward. That is, the equilibrium is going to set up more, it's going to lie to the right. It's going to set up more to the right. So you're going to get more HCl. Okay, well, what happens to the equilibrium shift, forward, reverse, or neither, if you remove some HCl? If you remove some HCl, what's going to happen is you're going to create a suction. And so it's going to suck to the right. So again, it's going to go forward. The equilibrium is going to shift to the right. Increased pressure. If you increase pressure, it's just like the one we looked at, number 8. If you increase pressure, where are there more moles of gas? Well, there's 1, 2 moles on this side, and there's 2 moles of gas on that side. If you increase pressure, it won't do a thing. No change, neither. Okay, if you decrease temperature, then what's going to happen is you're going to cut into this. So if you decrease temperature, it's just think of the opposite. If you increase temperature, you're going to make that really big, like that fat pimple, and you're going to blow lift. So if you decrease temperature, you're cutting into some of that, and you're going to suck to the right. And so if you pull off the HCl as it's formed, it's going to pull more to the right. If you suck off some of the heat as it forms, you're going to pull it to the right. So forward is the answer to that. Decreasing temperature also increases K. Decreasing temperature also will increase the value of the equilibrium constant. Anytime the K is big, it's pulling towards the right. You're making more product. But if you increase temperature, that would be number 11, H11H. If you increase temperature, the K value will go down. You'll have more reactants than you do products, and that's not good for industry. Okay, so if you increase temperature, it's going to make this bloat real big, and you're going to push to the left to relieve the stress. Le Chatelier says that's what happens. Okay, we're on E. Remove the H2. Oh, if you remove some H2, well, that's not good. If you remove some H2, that's going to create a suction and pull it to the left. So it's the reverse. More of this is going to break down and create the constituent elements, because if you remove some of that, it creates a suction in this direction. So then that would be, E would be reverse. F, if you decrease the pressure, if the pressure goes down, that won't change anything either, because you got 2 moles of gases over here, you got 2 moles of gases over there. So if you decrease the pressure, there'll be no change, neither. G, adding a catalyst. If you add a catalyst, it'll speed up the reaction, but it will not change the equilibrium position. It will not shift, so it's neither. H is increased temperature. We've already discussed that. If you increase temperature, this bloats up and it shoots reverse. The equilibrium shifts to the left, reverse. And then I is decreasing the system volume. Well, the system volume refers to the reactant vessel that you're doing this reaction in. So if you take that vessel and you squeeze it down like a balloon, if you squeeze it down, isn't that like increasing pressure? That's all that is. That's just another, I is the number, is another way of saying increasing pressure, like C. So if you increase pressure, there'll be no change, because there happens to be 2 moles over here and 2 moles over there, so we'll make neither. Number 12, how will it change the concentration of HCl? Well, anything on number 11 that said forward will make more HCl. Anything on number 11 that moves it forward will increase the K value. No, wrong. Only temperature changes will change the K value, because the equilibrium constant is simply a ratio. And if you change the concentrations of things, it's not going to change that ratio. So the equilibrium, changing the K value, the equilibrium constant, only happens when you change the temperature. And we've already discussed what's going to happen to the K value. If you increase temperature, then the K value will go down. If you decrease temperature, the K value will go up. You know what? That's 13 minutes. That's enough information. You should be able to do number 15. And those 5 problems in number 15A, B, C, D, and E is going to be your homework. But I'll do one more for you. Let's go look at 14. On number 14, what relative pressure, high or low pressure, would result in producing Morse carbon dioxide? Oh, do I hear you an answer? Oh, higher pressure, because on the left side, you've got 3 moles of gases, and on the right side, you've only got 2. So if you put higher pressure on those 3 moles, you always look at the greater number of moles side. Higher pressure is going to pop it to the right. It's going to relieve that stress. And then the hemoglobin thing on number 16, if you go up in a mountain at high altitude where the pressure is half of what it normally is, which way does it go? Well, on number 16, if you go up high on a mountain, it's going to push toward the right. No, it's going to lower pressure. It means the oxygen is the only gas on number 16. If it's lower pressure on the reactant side, it's going to suck to the left. So that's what's going to happen on number 16. So your hemoglobin, the equilibrium is going to set up with a lower hemoglobin concentration. That's probably not what you want. See ya.